welcome everybody that has joined us today for today's the second session of our education series. Yesterday we started with the topic basic seismic interpretation for reservoir identification, and engineer Idris Bukar did he did justice to the session. I want to welcome everybody that has joined. I can see our program chair, Amina Damandami here. Welcome, Ma. And every other person here. I can see our section director. So very quickly, I will give the floor to our section director, the person of Mr. Ere Iyala, to give the opening remarks. And immediately after his opening remarks, we go straight to the lecture. Please note that at the end of the session, everybody will have the opportunity to ask questions. So keep your questions in the chat session. And of course, we'll have a smooth lecture. So right now, please help me welcome our one and only and the most hardworking section director we know, Mr. Ere Iyala, for his opening remarks. Welcome, sir.
Okay, good morning, everyone. I also formally welcome you to this the second session of Education Series 3, which is in which Engineer Idris Bukar, who has been introduced. For those of you who were not here yesterday, he's a lecturer in the Department of Petroleum Engineering at the Abubakar Tafawa Balewa University, Bauchi. He also is a petroleum engineer with a master's degree in petroleum geosciences. I'm correct. He's taking us on a basic seismic interpretation for reservoir identification. But first, let me start by linking this to the SP mission, the basic mission of SP. Can you hear me? Hello?
We are hearing you.
Okay. The basic mission of SP
can.
is to collect, disseminate, and exchange technical information concerning the oil and gas industry, exploration, development, and production, and also to provide opportunities for professionals to enhance the technical knowledge. So in that light, we are taking it deeper. We're not focusing on just short trainings. We're focusing on taking it deeper and enabling cross-functional learning across disciplines, so that irrespective, SP is not only for engineers. Lawyers can learn this, economists can learn this, and any other discipline that is related or works alongside either as a core professional or a support individual for the oil and gas industry. So the aim of this series is to make sure that everybody has at least some basic knowledge of the main and support disciplines of the oil and gas industry. Having said that, I'd like to welcome everyone again. I implore you to learn as much as you can, because I can assure you that sometime in your interaction with the oil and gas industry, you come across these terms, and it will be nice if you have some basic idea. For the professionals for the professionals for which this is their core discipline, I advise you to take this and then go deeper. I would also encourage people to form study groups and research groups so that we can actually deepen our technical expertise and function better as professionals. I welcome all of you, and I hope that you have a great time listening to Dr. Engineer Idris Bukar. Thank you.
Thank you so much, sir. Okay, Engineer Idris, please, the floor is over to you. Thank you.
Thank you. Good morning, everyone. And that was a very nice opening remark by the section director, Mr. Ere Iyala. Oh yes, that's my video. My video on? I think it's on now.
You can go on, sir. We are hearing you.
Yes, I'm just about to share my screen so we can carry on. Yes, good morning again. And welcome to this second part of the Education Series 3 that we started yesterday. Today is more of a conclusion, if you like, of yesterday's session, and or a little recap and a conclusion, and then mostly for questions and answers. So yesterday we went through the presentation and we did talk about some of the things, most of what is in the outline. Acoustic impedance, reflection coefficient, the seismic trace, how we get the seismic trace, issue of polarity, etc. And I would just carry on from where I stopped, I think. Then maybe the recap would be in the sense of if anyone has a question that involves anything that I did talk about yesterday, then we can go back to it. So, yesterday we started. We talked about the first direct hydrocarbon indicator example, which is this Troll field in Norway, which shows us how we can see a flat spot and a bright spot on a seismic section as a way of identifying the flat spot being the fluid contact and the bright spot being the top of the reservoir, where we go from a shale to a lower AI sandstone, gas-bearing sandstone in this particular case. And we went on to show this second example, which is an offshore Nigeria case, where, like I said, it's probably the best I have seen in terms of DHI examples, published ones at least, where we have expressions of bright spots and flat spots. In fact, two flat spots, one for the oil-water contact and one for the gas-oil contact. Okay. So the aim of the aim of this whole presentation at the end of the day is to see how we can, one, identify the reservoirs from seismic data, and two, how we could, map some of these geometries of the reservoirs from seismic data. Okay. So, for instance, here, if we could go ahead and say we were trying to map this vertical section, right, of this reservoir, and perhaps we're going to, let's see, maybe I would use a whiteboard. I'll just create a space between my I'll create some space on the PowerPoint. So if you look at it here, let me create some space so I can draw some of these. So I can draw my own interpretation of Just hold on a minute. Good. So with this space here now, if I wanted to map what this reservoir would look like in this vertical section, if I wanted to just sketch it, I would say, like I said, is a tilted fault block. So we would probably have, you know, something going like this. Right? And then going like this. Okay, so this is the basic geometry of the reservoir from this image. However, we can also include the fluid contacts. So here we have, well, the gas oil contact, right? But then, as you can see, these are two units stacked on top of the other. And I would say that there is a shale here in between them. I mean, it's kind of obvious from the seismic section why there's supposed to be a shale, but it is also a large part of why we have this second yellow bright spot from the oil. Okay, so out here we have shale encasing everything, right? So, and then in here, we have gas up here. Then let's say oil to this point. So oil here, right? And then the water leg is down here. Now, if we looked at the DHIs here, we would see that up here, for instance, so up here, we're going from shale to a gas sand, right? So if I draw again my AI graph, increasing AI, then we're going from, so we have shale here, water, oil here, sorry, water here, oil here, right? And then gas at the end. So we're going from shale straight into a gas sand. So you see the size of the drop in acoustic impedance, which is what gives us this yellow bright spot at the top of where we go from shale to gas. Okay, so this is taken care of. Then from this point here where the yellow sort of dims into a red, we're going from shale to oil sand, right? So we're going from here to here. So it's a smaller drop in acoustic impedance. So it's a bright spot, but of a lower intensity, right? And then that's what gives us the bright spot on this side, okay? So, and then onto this next unit, we're going from oil, so we're going from a shale, this shale sandwiched in between the two sand units, to oil. So I suspect that this shale here is not the same as this shale that is outside, okay? This is what I would say is a stiffer shale. Because, like I said, this whole DHI business is all relative. If a shale is given the same sort of bright spot between it and oil, and then another shale is giving a similar bright spot between it and gas, then obviously this shale that is in here has to be higher so that we can sort of maintain the, so maybe shale 2 would be somewhere here. So shale 2 is going from here to here, right? Such that at the end of the day, the size of this drop and the size of this drop are similar, even though this is going from shale to oil, this is going from shale to gas. But if this shale is of a higher stiffness, then we can see how that happens, okay? So, because another thing that would prove that is that up here, we're also going from shale to oil. But because it's this shale that I say should be of a lower AI to oil, you see the bright spot is not very bright, okay? So it's all very, very relative, so you have to learn to look at it in a relative sense. That you see a very bright reflector, a bright event, or dim event, whatever it is, on a seismic section, is telling you something about both the top layer and the bottom layer. It's not telling you something about just one layer. It's a relative thing. Okay, so shale 1, shale 2, okay? And then we have, and then here we're going from oil to water, and like I mentioned yesterday, this suggests that we have a hydraulic communication between these two units, because the fluid contact goes across the two units as a flat spot, okay? So we end up with something like this in vertical section, and we say, another thing, like I mentioned, is that the hydraulic communication could be as a result of, or how do I put it? The seismic cannot really show us where the hydraulic communication is taking place, right? Because all it takes is, no matter how little, some communication between it. Because think about, this reservoir has been there for, millions of years in geologic time. So it's had time, the fluid has had time over this very long period to sort of equilibrate between the two units, okay? So even, if it's a small carrier bed, if you like, in between these two units, over geologic time, everything will sort of equal out and would have this fluid contact, suggesting that it's one reservoir, okay? So this is the expression, I should say, of what we're interpreting from this seismic data. Okay, all right. So going back to the troll field again, so that one is, we just showed how you could get a sort of vertical or cross-section view of a reservoir, a cross-sectional interpretation. And now this is now a sort of mapping, okay? And this is the map of the troll field in the Norwegian North Sea that we talked about, okay? And these are two, on the right, on the southeastern corner, we have the troll east, which is the one we have been showing yesterday, which is which is a gas field. And then the troll west, which is here, is oil and gas. If you can see the shading, has red and green in the shading, okay? And this is the legend is all on this area here. So if you went into a seismic, 3D seismic data set of this troll field and you started interpreting, the goal is to be able to map something that looks like this at the end of the day, okay? Because obviously seismic is the best thing we can use to map these reservoirs. I don't think anything else comes close. So, and then you can see some of the details about the field and what have you. And I'll come back to this figure. So this is one of the sections, right, from yesterday. We've not shown this. And basically, this is the red here. Remember, we're working in European polarity. So the red here, which is denoting a soft event, because it's the other way around, is the top of the reservoir. And the blue here, which we showed in the textbook image that we showed yesterday, is your gas water contact, so your fluid contact. You see, it terminates here against the top of the reservoir on this end here. Okay, so the idea is if you map this in any sort of seismic interpretation software, then you would follow this interpretation. Where's my color? So you'd follow this sort of here. Okay, and you go, obviously one of the ways to do it would have been better if I was probably doing this as a practical, but anyways, is you go inline by inline. So you probably jump in 10 inlines or 10 cross lines, you're going like that and you're interpreting every line. So it's a sort of 2D interpretation. You interpret it on this line, you step to the next 10 lines or 5 lines or 20 lines, and then you interpret it again and you keep going, and then you do the same thing from the cross-line perspective. Remember I said they are orthogonal. And then hopefully the map will begin to appear. So you see this is an interpretation of this previous top reservoir of the troll. And you see how the interpretation lines go. And then, so this is where we are on an inline here. Notice how this top number does not change, okay? And then the bottom number changes because the cross lines are going perpendicular. And then you can also go to the cross line. We're now on a cross line, right? The bottom number is the one that is constant now, and the inline is moving. Two-way time, before I forget. Okay, so you map that in both inline, cross line, and so you do something like this, right? And then you see, again, this is the expression of the top of the reservoir, right? And this is the fluid contact, right? So you go this way, and then when you do this throughout the data set, as much as you can follow it, right? You begin to get a sort of interpretation like this when you look at it from the top, okay? And the shape begins to appear, right, of the troll field map that we're sort of trying to map here. The shape sort of starts to emerge, okay? Of course, this map was, done by experts, and I'm sure they must have done a lot of other additional techniques. They didn't just go into into an interpretation software and just mapped it as a layman would do like this. So you have this. And another thing which I will show in probably the next example is that sometimes you lose your reflectors, right? Because again, it is a relative thing. So on the seismic, you're following your reflectors, and maybe you get to a point where the encasing shale is of a closer AI to the reservoir, and so the reflector sort of starts to dim out, right? Or for whatever reason you lose your reflectors, then your wells come in very handy, because see, over time, this gives you at the exploration stage, this gives you a sort of rough size of the reservoir. But with your wells, when you tie your wells to the seismic, your wells, wherever you lose your horizons, your wells will sort of put you back on track. Basically tell you, it is this one now, you know, because there's a well passing through there, and there's what we call a well top that is marking that place, telling you, carry on going in that direction. They're not always accurate because, you know, we had to convert the, you know, the placement of the well tops are not always right on the horizon, but at least they would help guide you, because seismic is depth converted, right? And we use a velocity model to do that because it's originally in time. So the shape begins to emerge. And maybe if you do some little more tweaking or some, if you probably like this, you know, maybe you're seeing more of the shape coming out now. And you can see, I don't know, someone seems to be drawing on my screen. Anyways, so yes, so this is what we are sort of trying to come up with here, the Troll East field, the gas field. And this is sort of a layman's approach. You know, you could probably do this in a few hours to get to this point. And then you populate all the in-betweens to make it a sort of three-dimensional from this mesh structure, which you did from, you know, interpreting an inline going like this, sorry, a cross line going like this, and then an inline going like this, and then you sort of keep getting this until you get the shape coming out like this, okay? So this is what this would give you when you keep doing it. All right. So, and another thing, let's see. Yes. So this is another field, right? This is the Volve field. Again, Norwegian North Sea. I seem to like these Norwegian data sets, and you know, there's a reason. Here, this is not two-way time, right? This is depth. So this is basically TVDSS. Okay, true vertical depth, subsea. And you can see the seismic here is not as expressive as the one we just finished looking at. Because anytime I illustrate seismic interpretation with really good data sets like Troll and what have you, I feel like I am doing a disservice to the person I'm illustrating to, because I'm probably giving them the impression that this is how all seismic data sets are going to look. This is how good they're going to look, how clear and obvious. But, you know, you probably see DHIs 20% of the time, right? Or 30%, I don't know. But it's a small percentage. a lot of the time they are not very, you don't get to see them. Which is why we find these examples, even the textbooks, they hold on to them and they use them to show the expressions of these direct hydrocarbon indicators. But really, sometimes it's just an issue of your wells guiding you. Because when you don't have a direct hydrocarbon indicator, then, let's say you have, like in this particular field, there are so many horizons to map, right? There's the top Hugin, there's the top Sleipner, there's the top Shetland group. There's so many, horizons to map out. And, you probably see maybe a strong expression on one of them. And then the rest are just horizons that are sort of faint. And you now have to depend on your wells. Okay? Of course, to now use your wells to guide your interpretation, you need one of the two to happen. Either your wells to be in time, if your seismic has not been converted to time, or your seismic to have been depth converted, which is the case here. Okay, the seismic is in depth, so this is meters. Yeah, so we're getting close to about 10,000 meters at 3,000, 10,000 feet at 3,000 meters here. Okay, so your wells are now probably now telling you, if you're here and you don't know what you're looking for, your horizon, these two markers, which correspond to the well tops of the particular horizon we're interested in, would tell you to probably put your horizons here, all right, and here. See, this is what real data looks like. It's not exact, because like I said, differences in, or how do I put it, imperfections in the velocity model that was used to convert the seismic to depth and what have you. So many things could make this thing look, or even the what's it called? The frequencies, right? That would make, because think about it. Every reflector here, every reflection is representing a boundary. So a boundary does not have a thickness. It's a line, right? It's the bed that has a thickness. So if this is layer 1, layer 2, a boundary is a line, effectively. But this is what seismic is telling us is representing that line. I mean, if you take this is probably somewhere on the order of, if this is 200 meters, so this is probably somewhere on the order of a quarter of that, right? So 50 meters. 50 meters, a 50-meter wide expression of a line, basically, right? So this is again exposing some of the imperfections of seismic data, okay? So, but at the end of the day, your wells will help guide you to follow your horizon. So you follow it here, and when you lose it somewhere, like when you get to probably some area like this where you don't really know what is what, then if you have another well in the location, you are saved, okay, to kind of keep you back on track. And this is the professionally done seismic horizon or seismic reservoir mapping for the Volve field, which I will also show on the Norwegian North Sea map. Okay, this is professionally done. I think after, I think this is even showing both the top and the base. Okay, in the 3D view, And these are the wells, as you can see, sort of going into this dome structure here, where the reservoir is. They mapped it all the way throughout the seismic data set, but really this is where the accumulation is. So they're mapping the top of a particular what's it called? To a particular horizon or a top of a unit, okay, a geological unit. So, but the reservoir is, the accumulation is up to the spill point here, okay, just outside of the dome. So you see how, in fact, there's a well sort of going all the way into this area here, which I found out was a well they did for disposal of gas, I think, or something. Okay, so you could sort of say this is the expression of the field on the seismic, and you know, I think they look kind of close enough. I don't know, because this is the shape of the field on the map. Let me go to this map so I can show some of the things I've been trying to I find this quite interesting that we have, you know, this is basically open access. This is accessible to everyone. This is the map of the sort of fields in the Norwegian continental shelf. And this is how I got the trawl field, right? So you go trawl, field trawl, and it takes you there. And the interesting thing is, it doesn't just show the blocks or what have you. It really actually shows the shapes of the reservoirs as mapped, you know, and what is in there, and some little information, discovery year, and what have you. Okay, so there are so many other fields, and you can even look at the platforms, how much remaining reserves the owners. So this is quite democratized, if you like. You can even find out where the Troll A platform is sort of located. So just right here, where this little call out starts from. So sort of top of the structure, if you look at the map, you look at the interpretation, okay? So that's where that concrete structure is sitting. And also the valve, which I showed just now, you can also find, oh yeah, I just saw something. Let me go back to some of the details about the platform. You see how the kind of platform, conduit 4 shafts in service, started in 96, water depth of 302 meters, which is something around what we calculated yesterday. We said the water depth is around 300 to 330 across the field. So it is the platform is particularly sitting at a water depth where it is 302 meters on the shallower side of things. And it has a design lifetime of 70 years, okay? I like to kind of move in between some of these seismic and some of these facilities and what have you. So the engineers don't kind of feel too, feel they're in a strange land of us talking about reflection coefficients and what have you. So yeah, and the valve, which is where I got that map from, and I decided to just show, it's here. Okay, so started in 2008, it's shut down. I think it's ran till 2016 for 8 years, and it's an oil field, hence the green color of the field. Okay, I kind of wish maybe every basin in the world, or at least in places we're interested in, could have all this kind of information available. I guess maybe in some places it's probably even for security reasons and what have you. Sleipner is next to Volve and what have you. Okay, so yeah, this is so these field shapes are really the expression of, this is Johann Sverdrup field here. So these are the expressions really of the shapes of the fields as mapped from seismic. We also have the blocks shown. Okay, so try and go back to my PowerPoint slideshow. Yeah, so I guess this is the conclusion I said I was going to do for today, and probably start taking questions now if you have any. Okay, all right, thank you. This is the end of my presentation. Welcome any questions from the audience.
Thank you very much, sir. Thank you very much. So please, if you have questions, we are very much open to reading them. Kindly drop them in the chat box, and our lecturer will do justice to your questions. So I believe everybody fully understands the topic. Okay, sir. So I think, okay, they have a question from Amina. Can the size of a reservoir be determined by only seismic?
Okay, yeah, that's a good question. You have, seismic would give you a rough estimate of the size, right? So when you're doing a seismic exploration, when you're using seismic for an exploration exercise, you would use it to sort of do some volumetrics, basic volumetrics, right? We do our gross rock volume, our net to gross, our porosity, our fluid saturations. We put together everything to get our oil in place and what have you. You would use seismic to do that, but really you're going to have quite a large uncertainty, right? Because I mentioned a few things. The things that go into our oil in place calculation: gross rock volume, right? Porosity, net to gross, right? Fluid saturation. These things, you will see that you will find out that the one that has by far the highest uncertainty is the gross rock volume, which is the one you get from seismic, right? Because, like I said, the issue of resolution and what have you, if you're deeper in the seismic section, seismic reflections can broaden out because of the lower frequencies that get to that deeper part, and show you a unit to be thicker than it actually is. So would add to that uncertainty. So really, your seismic would give you an idea, but you would have quite a large uncertainty. So that's where you now do your probabilistic, P10, P50, P90, and what have you. Okay, so yeah, we cannot use only seismic to determine, but we can have an idea. But if you use only seismic, you could be off by quite a large margin, and perhaps that margin could be the margin that could determine whether or not that prospect is developed or abandoned. So yes, so you now put together your seismic, and then you do your well tests, your well test analysis, and what have you. And then when you put all of that information together, then you have a more, and then when you start getting production data, doing decline curve and what have you, you start, refining your estimates. So the other question is how we store seismic data. Yeah, so, from the field, we record them on tapes, but really after all the processing has been done, they go from all the magnetic tapes to a SEG format data, which is, data you can open on your computer in a seismic interpretation software or what have you. Okay, so it's as SEG or SEG being the Society for Exploration Geophysicists, and or ZGY and what have you. But originally when it is recorded in the field, it is stored on magnetic tapes. Okay. Some tips on selecting locations for exploration and appraisal wells by simply looking at the seismic. Well, if you have a DHI expression like we have on the troll field, then you basically just put, right? I would just anywhere here, but usually we like to put our first wells at the top of the structure, right? So if there's any, the top, where if there's a gas cap, we would see the gas cap and then penetrate the oil leg and the water as well. So yeah, just if you have a DHI expression, of course, if you don't have a DHI but you've mapped it, then again, same old logic of putting it at the top of the structure, because the fluid rises, the hydrocarbons rise to the top of the structure, right? So like what they've done here, okay? What more? What are the parameters needed before you get a manual plot of seismic section? I'm not sure I understand this question, really. I don't know if you could clarify, but before then I'll go on to the next question. So how are we able to carry out a history matching using time-lapse seismic data? Now, you started hearing engineers talking now, and to do history matching and what have you. So time-lapse seismic is 4D seismic, basically, right? So basically we take seismic, we have a baseline survey. So the first survey that you take is your baseline, and then I think there's a time-lapse session coming up next weekend or something like that. Anyways, so you have the baseline survey. Maybe you took it in, let's say 2000, and then maybe after a few years you have maybe in 2005 you take another 3D survey, right? And then maybe in 2010 you take another 3D survey. Those are called the monitor surveys, right? So you're sort of monitoring what is happening from the baseline. And then that is now what makes the fourth dimension, the time that you're going on. So when we have a time-lapse seismic data, of course, you can do your history matching, because even by looking at the seismic data, we're seeing, for instance, one of the best things that you would see from a time-lapse data is your fluid movement, basically. Where has been swept, where has not been swept, and what have you. So it would give you it will guide you as to sort of which wells, would be best suited for your history matching in the whole field, right? Because some places you find out you even need to do infill drilling, because for some reason there are some flow barriers, and what you expect to have swept has not been swept, So yeah, time lapse is quite, it's probably, after the 3D seismic itself, it's probably the best thing, in seismic, because it really gives you a time lapse view of it over time. So yeah, you can. What are the parameters needed before you get a manual plot? I suppose the person is asking of maybe manual interpretation that I showed, but I guess that is parameters needed, where if you know your polarity, if you know what you are looking at, what colors represent what, and you have a DHI or not, then you can just start following your horizons, and I don't think there are any parameters per se, okay? And the person has not sort of, after seismic data and you want to have a manual plot boundary, what do you look out for on the seismic to guide your plot? You want to have a manual plot boundary. Oh, okay. So I guess the person is asking for how, you sort of bound these fields. You sort of draw a polygon around the field. So usually we map the field up to, in seismic, like I've observed that on the, what's it called? On the maps that I showed, like this one, or the troll, they are mapping the field to the fluid contact or the spill point, right? Of course, in petroleum engineering, we know that the water leg is part of the reservoir, right? But it seems that they are mapping it up to either the spill point or the fluid contact and what have you. So I suppose if it depends what you want to do. If you, for an exploration exercise, you're really just mapping up to the fluid contact. So your boundary would be set at, so for instance, here, another thing I could do is, if I knew where the fluid contact is, I could create a flat horizon and fix the depth of that horizon to that particular figure, and then put it in here. And then it will basically slice off anything that is below it. And then whatever is left of the shape is what I can now follow as this is the map of my, top reservoir, okay, where there are hydrocarbons. So yeah, depends on either the fluid contact or the spill point of the structure. Okay, so that's what guides you. I think troll here also is down to because if you observed, I did not go down the water leg, right? And if you did that, you would probably get a shape that is bigger than the actual shape of the field. So I suppose they are mapping only the hydrocarbon bearing section, but for reservoir engineering purposes, the water leg is quite an important part of. But then even when you are doing your, what's it called, volumetrics, you do it at least at a very basic level. You do it from the fluid contact to the top of the structure. Okay, I think that's all the questions. I said yesterday that today's session is going to be short, and I think we've managed to squeeze everything into an hour. Yeah, in the absence of any more questions, I guess I'll hand over the stage to the moderator.
Okay. Thank you very, very much, sir. We really appreciate. For those who may want the slide and the video for yesterday's session and today's session, kindly request it at spabuja-info@gmail.com. And of course, you'll be updated of every other activities you may have. At this moment, ladies and gentlemen, please permit me to once again invite our 5-star section director, the one and only Mr. Ere Iyala, for the closing remarks. Mr. Ere Iyala, over to you, sir. Mr. Ere Iyala, are you there, sir? Okay, I guess maybe he's not by his phone. So I can see our program chair is still here. Program chairman, please help us with a closing remarks since Mr. Ere is not by.
Okay, good morning, everyone, and thank you for joining our program. But let me call Engineer Yetunde to please give the closing remark. She's a very active member of Abuja section. Engineer Yetunde, please give us a closing remark. Thank you. She left. Okay. And maybe network problem. Hello? Okay, I think she's having network problem. Thank you very much. It was a very lecture, and we've learned a lot. And we'll keep rolling out sessions like this that will help us in understanding the oil and gas industry much better. Engineer Idris, this was a very insightful lecture, and we thank you so much for agreeing to give us this lecture, and we look forward to having more of such from you. You're truly an expert in your field, and would really want you to share your knowledge with us as we go along. And you can also help us by mentoring our upcoming students so that they can also be guided by you. Already the faculty advisor in ATBU. Thank you for all the good work you're doing. To everyone who has joined this session, we thank you very much for making out time to join us. I noticed some of my people from DPR, have joined. Thank you very much for the support and for the encouragement. And I would urge each of you to give us, if you have any area where you need clarification or some area you need a lecture on, you can please reach out to us, send an email to that address that the moderator gave, and we'll see what we can do. That is what the SPE mission, to disseminate and share technical knowledge. So if you have any areas that you need, especially for us here in Abuja, the North, we don't really have opportunities for practical experience in the oil and gas industry. So these are the ways where we can use to fill that gap. So we look forward to some feedback from all of you. And thank you, moderator Apan. You've been a strong support to the section. I'm not sure we'll be able to do all of these programs without you. So thank you very much. And thank you to everyone. Thank you, board members, Abuja section. Thank you, all members, Abuja section. And thank you, all SPE members, Nigeria. Thank you very much, Engineer Idris. Hello.
Okay. Thank you so much, Ma. Thank you very much, Ma.
All right.
Okay. So we come to the end of today's session. Please kindly note that next week, the 18th of September 2020 on Friday, we have a technical session which will be led by the Senior Development Planner of Southern Nigeria and SPE Lagos Section Director, Ogogo Efiom. She is going to be dissecting the topic, the value of time-lapse seismic in a deep water field. Of course, the meeting link and the password will be sent to everybody via our social media platforms. So please kindly endeavor to attend. Once again, thank you, distinguished invited guests, for joining this session. And of course, to have a lovely Saturday. See you next week, Friday.